highlight. For example, if you are asked to excite a certain mode of a wave in a waveguide, is something we had touched on. We just needed some revisions. For example, you are asked to excite a TE10. We know that we need to place the probe at the point that will give us the maximum amplitude of that wave. So, for example, we can have just hold on. I think I need the I need to go to the file itself. So you're asked to excite TE10. We need to place the probe at the point of maximum amplitude. Let's say you have Y. So TE10 means M is equal to 1. The half of variation, N is equal to 0. So if that's Y, it's no variation on Y, but on X, and given a field, we had seen that actually you're supposed to place the probe at half X. So you'll have the E field there. This is on X. So if that's half X, then it means the dimension of the waveguide is somewhere there. So that's the point A, B. Of course, the H field is solenoidal, it's perpendicular to the E field. You can sketch here H field. So that will be the excitation for a TE. So the point 0 is in this here of your waveguide, a rectangular waveguide. Z is in the other direction. So that will be excitation over TE10. What about a TM or a TE11? How would you place your probe? So for 11, it means both half-wave variations exist for M and N, where M is equal to 1. Let's say TM1. So if we are to place that probe at half Y and half X, so you need to try to draw it in 3D. So you have Y. We know that you are exciting it with a half variation, so it means at the middle somewhere. So if you are to do that, then it means the E field. So here is B. At this point is B over 2. Are you inserting that? We need to draw the 3D. So it means then this will be Z. So X at this point here, on the other side will also be X over 2. So then the E field you'll have your E field there. That will be TM11. What about the variation? How do you plot? How do you show the field variations that we are talking about? So we can also get another mode like maybe TM22 or 23 or 32. So let's say you want to view these are field variations that we're talking about. 32. Let's have a cross section, maybe X and Y. So here it means TE32 is a M is 3, N is equal to 2. Okay, so we can have Y, X. So it's a ratio of 3 to 2. So if we have one here, we need half of that, maybe up to here. The other one should be longer. So if they have field variations, we will need just 2 here. So we have that, have that, have that. M should be 3, so N is equal to 2. M is equal to 3 on X. So in that case, so we have 3 this side, so we have 2 and the other 1/4. This will be 3 half waves. Then it should be 3 all the time, so this is so here will be, then the other side. Sorry. So here you can have, so you can see M is always 3 on X, N is 2 half waves. So if you decide to say that fields are varying like this, if they're converging here, sorry. So that means then even that is converging there. So it means they must be leaving here and entering. So if they're entering, it means they're leaving. So it's same direction. This must be downwards. If that is down, then this up. That must also be up, same direction. We are leaving. So you can always draw. So converging there. No, sorry. So it means leaving here. Just entering there. Now what's this? Entering there. So that is the depiction of the half-wave variations for M is equal to 3 and N equal to 2. Okay, so what if you wanted to do one for, say, TE11, TM11? How would you have the half-wave variations for 1, 1? It means here M is equal to 1, equal to 2. Both 1, not 2. M1, N1. Then you can choose to have y-axis up or x. So you have 1, 1, so it means simple square. So if it's 1, 1, so we are targeting the middle. So you can decide they're diverging from here, meaning they'll be entering there. Any question on that? Somebody has something? No. Yes, Samuel.
Yes. How would we excite, for example, a TE21 mode?
A TE21. So I've shown you the excitation for a TE10, isn't it? And a TM11.
Yes.
So you can, because if you, is it here I was working with? I've lost my document. Was it here? Not that. This is the document I was working with. It looks like I didn't save it. You see this one? Okay. So you have a TE10. You saw the location on, we just want to produce a single M at the location where we know that the maximum wave variation, the maximum amplitude will be obtained. Remember, you can put that probe anywhere, but here it's just targeting the maximum amplitude. So you'll have variations on X. So that's why we're putting it at X is equal to half, but you could place it at anywhere on that X-axis, only that the amplitude of the wave, so if you look at the wave equations, will not be maximum. Then, if you want to do more than one, excitation of more than one wave, so we have the energy, because we need to write the wave equation. If you remember, do we have any here? The general expression for, so that you can see what M and N really means. Do we have any? Are you seeing that one there? Samuel? Am I audible? Okay.
Yes, I
So,
can.
yeah, so this is M. What is M here? M is equal to? Can somebody tell me what M is on this equation? You can have your microphone on, Samuel, so that we go first.
Yeah, it's 1.
M is 1. And N? The value for N? N is equal to 3. What about the amplitude of that signal, of H? Amplitude?
2.
Is 2. How will M, if we were to put M is equal to 2 on that value for h, what will change if m is equal to 2?
It will vanish.
It would vanish. Are you sure? Remember, we x is arbitrary. You are looking at the 2 pi. Remember, a is also arbitrary, like in this case is 1.5. So sine of that angle, it doesn't really vanish. If you have m is equal to 2, it will be sine of 2 pi x over a. So if you excite at x is equal to a over 2, if you excite at x is equal to a over 2, what happens? So this, if you excite at a over 2, which we are saying half of the waveguide, isn't it? That's when that value vanishes. But if you excite the probe at a certain point, which is not x is equal to a over 2, what happens? So you have sine 2 pi x 2 pi x over some value. Let's say x is not equal to a over 2. So you move it to a over 3. X is a over 2, so we can erase this one. So here we have 2 pi x is actually we're not supposed to change that lower one. We just have it as a, then we say x is not a over 2, but we put it at x is a over. You move the probe, a over 3. So what happens? This will be sine
2 pi over 3.
which is what angle?
It's 120 degrees.
120. So it will be sine 60, isn't it? Is that so? So that does tell
Yes.
you, yeah. Does that tell you now, apart from just placing the probe, which will give you a maximum if you're talking about is 1020, 1011, you can see that you now decide whatever you want to excite. If you want to excite a higher mode, what do you change? The location of the probe, isn't it?
Yes.
Yeah. So that's how you excite different modes, so that you don't have your fields cancelling out. So you work with this location here. And then you try to get what will give you the max, what location will give you the maximum value. Because apart from this is the signal. You can see this still speaks to the amplitude, isn't it? Is it clear how you excite different modes?
Yes.
Yeah, you play with the location of that probe for different modes. Okay, so that's now, yeah. If you want to go deeper into it, that's what you do.
Excuse me.
Yeah.
There was a controversy, just different ideas
Yeah.
on the type of mode that that was being excited in that particular question.
In a particular question.
In that particular question, whether it was TE113 or TM13 or both, was that. Maybe if you could yourself just to clarify that.
Oh, can you tell whether it's a TM or TE? That's the question.
Yeah, absolutely. That was the question, but others were saying it was both TE113 and TM13. Others were saying it was TE13. So maybe
Others were saying it is. Come again.
others were saying it was TE13
Hmm.
and TM13.
Mhm.
And maybe others said the controversial opinion that it was TE13. Maybe if you can just help us to clarify that.
Okay. The controversy is what I don't get. You're saying they were saying it is TM13 or TE13, and others were saying it is TE13, not TM. Is that what you're saying?
Others were saying it was both TE13 and TM13.
And others?
And others were saying it was TE13.
Ah, okay.
Yeah.
Fine, but you can see even from the question itself, we are saying state the modes of operation. It can be TE or TM, because you can't tell from here, isn't it? Right? Can you tell? If I give you HZ, if I give you HZ, can you tell whether it is TE or TM? What is the definition for a TM mode and a TE mode? See, that's how we try to answer that question, isn't it? For in this case, where we are given HX, in a transverse electric, what does not exist? Can leave your microphone on so that we go quickly. What does not exist in a transverse magnetic mode? From the name.
The axial component of E.
Yeah?
EX.
If I gave you a TE mode, will HX exist? TE mode is transverse electric. What does not exist? Maybe you can answer from that. In the definition of a TM mode, we only know that EZ will be 0 for a TE mode, isn't it? Because we are saying it is transverse electric. If it is transverse, it means the axial component is equal to 0. Only the axial component. So if it was EZ, and we know that EZ is 0 for a TE mode. TM, what is 0? For a TM mode, what is equal to 0?
HZ.
HZ, isn't it? So HX, HY, those ones still exist. So this one, where you're just given HX, it could be a TE or it could be a TE or a TM. We can't tell from the expression. So we should agree that it can be either of them. I don't know whether it's clear.
Yes.
All right. There's something I wanted to highlight apart from the excitation before 1 hour. This is the last. It looks like I will not be there on Tuesday, but the CAT is there. It will be conducted properly. So let's highlight. Actually, we are not highlighting this because it is in the CAT. It's just for your knowledge, and also not saying they are not in the CAT. So there was something else on when you have a dielectric inside a waveguide. correct. So what is the power flow? How does power flow inside this waveguide? So we will have radiation losses. If you excite, let's say you're exciting at a certain point for a certain mode. So you'll have radiation losses, conduction losses, and due to the walls and also due to the dielectric. So the power flow inside here would be such that at any point inside there, from the point of injection, you're going to lose some power. So if you have Pi at the start in, how do you get the power loss? So the power flow, we can decide and say is exponential. So it's P. So this will be P at any point. It's equal to Pi 2 times attenuation constant at a distance Z. So it means the power loss inside here would be P at the start minus P at that point. So it means we'll have Pi minus Pz. And that would be Pi 1 minus 2 times Z. But how do you consider whether the loss due to the dielectric is sufficient enough to be considered? Because we have a very complicated equation for the power loss due to the dielectric and conduction. So you look at the ratio between the conduction current density and the current density and the dielectric. So this ratio, what's the name of this ratio? We can express this in terms of the conductivity, and also this other one in terms of the dielectric, which can be reduced to sigma over omega epsilon, because D is equal to epsilon times E. So what is the name of this ratio here?
It's the loss tangent.
Yeah, so that's the loss tangent. So you can check from the loss tangent whether it is important to use the losses, the attenuation constant due to the dielectric and the conduction. You could also be given some power in terms of the received power. So you just manipulate this function here to be able to compute power inside that waveguide. What if the waveguide was glass? So if you're like let's say fiber, you're working with fiber, optic fiber. Let's say the refractive index of fiber eta is equal to 1.5. And you are told that probably you are injecting a wave at a certain frequency, f0. So the question is, the wavelength of that signal in the glass, is it going to be shorter or longer? So we can compute the speed of this wave in this glass. I think my space is done. So we can have the speed, so V, in terms of refractive index, We can define refractive index as V over. So we can say the refractive index is the speed in free space over V in the glass. So we get V in the glass, and then we find the computation for, we compute the wavelength. So this will be Vg over F naught. And Vg we can see is C over V, C over eta, F naught. So compare lambda G and lambda naught. Which one is higher? Which wavelength is higher? Lambda naught definitely is, sorry. C over F naught. Which wavelength is larger than the other? Between lambda G and lambda naught, which one is larger? We have eta, the refractive index in fiber glass, being 1.5. Anyone who wants to help us?
Lambda naught is large.
Lambda naught is larger, isn't it?
Yeah.
So in glass, we'll have the reduced wavelength. There was something to do with quality factor. You had optional questions here. And by the way, in the CAT, don't forget to see the instruction. There will be a number of questions, but you choose just 50% of them. So if section 1 has 2 questions, you take one of your choice for the CAT. All right, so here you had been asked to define the quality factor as the number of oscillations before energy decreases to e raised to -1 at a time t is equal to 1 over 2 alpha. Then you proceed and show that for lamp circuits RLC, you can have Q as root of L over C over R. And that one we discussed. So how do you sketch this wave? We are saying that with time, the oscillations of this wave reduces, the amplitude reduces to e raised to -1. So we are saying at that point, we get that ratio and call the number of oscillations that happen until that point is reached as the quality factor. So it means if you're saying the number of oscillations, the quality factor can actually be a very big number for different cavities. So it means for us to define it like that, it means we have defined the power or energy inside the cavity. So that we can see at t is equal to 1 over 2 alpha, that's when we have that energy reducing to e raised to -1. And if we get the energy with time, then we get the power loss, which is 2 alpha. So by expressing 2 alpha in terms of PD, the power loss, and the energy stored, that's when we computed quality factor. Otherwise, the quality factor is the number of oscillations in radians. So you can have Q is equal to omega t. Then you just replace that t, because at that point we're defining Q, t is equal to 1 over 2 alpha. So we can see already that Q is equal to omega over 2 alpha. But again, you may want to define that to alpha, which we have seen, dWt over dt gives us PD over Wt. So if you replace that, then you have the definition for Q quality factor, which we know, omega times WT over PD. But because omega is 2 pi F, so you can have 2 pi over T times WT over PD. So that's why we're saying is the ratio for the energy stored to 2 pi times energy stored over the power loss per oscillation, because we have the period T. So that's how we define the quality factor. Now the question is, sometimes due to the characteristics of the environment or the dielectric, the temperature changes in a dielectric which is placed inside a cavity may lead to a complex permittivity. Complex permittivity. So if the quality factor that we're talking about here is just a number. So when a complex permittivity is there, it's going to complicate the wave dynamics. So it means we have permittivity now being E plus or minus J, some other value, let's say that. So if that is the way it means, then the real component is working in a different direction, and this other perpendicular component is also producing some effect in terms of the quality factor. So number one, let's sketch. We have just said the quality factor is defined with time as the number of oscillations at which the amplitude reduces to a certain value. So it means we could have right? So you have that A naught. Then we have a certain, let's say here, this is where we have A naught E raised to 1. So what is the quality factor in this one? You count number of oscillations, isn't it? So you have quality factor 1, 2, almost 3, maybe 2.5. So you can count the number of oscillations, so quality factor is 2.5 in that case. I hope it's clear what we are trying to explain by this quality factor that we're looking at. So if there's a complex permittivity, so it means we are going to have two values for Q, which is going to affect this oscillation. So number one, you'll have now Q due to the electric, and another Q due to the conduction on the walls. So here we normally have we treat them in parallel. So we have the total Q as, actually we just write it straight away. One over total Q is 1 over Q due to C plus Q due to D. Q due to C we know. For example, for a cubical cavity, we know Q, C. Anyone remembers? It's not good to cram it, but it's normally, because it's a cube, the dimension is just A over 3 times the skin depth. So we have QC, so you can compute that one based on the factors that you are given. What about QD? If the permittivity is complex, then now we have QD is going to be the ratio of the real component over the imaginary component. Okay, then you use this one to compute. By intuition, do you think the final Q is going to be reduced or increased when there is this complex permittivity? or by derivation? Is Q going to reduce or to increase? This one you can see Q, we said. QC, QD, and Q, C plus QD. All right, so normally the complex, the imaginary part is so small. It's so small because the effect where the humidity or the temperature changes are making the permittivity complex. It makes that epsilon double apostrophe very, very small. So in that case, then it means it is going to have an effect of reducing the overall quality of that cavity. So Q that we are going to have is going to end up being very small, where the product is much smaller than the sum. Okay, skin depth, obviously we have the equation for the skin depth. It's normally just 1 over root of pi mu F times the conductivity. Okay, I'm not seeing anything that is going to be outside this tutorial. I don't think so. And the revisions that we have had. So just prepare for the CAT properly. I hope all of you will do well. Don't try to copy from anywhere, and cooperate with the lecturer will be there to give out the CAT on Tuesday. In terms of passive and active devices, remember we agreed this just about, you have to sketch it, give us the mode of operation, how does it operate by principle, any application areas, what is the difference, like Faraday rotation, what is that? You need to, at least you understand the concept. And then if I gave you a gyrate and isolator, can you draw them and describe the difference? What about a magnetron? Any application of that, or a klystron, bunching process. Those are the key principles that are there for passive and active devices. And you have your tutorials, your answers to the tutorials that you gave. You can use that too. For number 4 here, I just want you to remember that be keen. I will be testing keenness on that number 4. So just be keen on how these values were derived. If you master, if you understand, the formulae are there. Remember in 5th year, just doing the applications. So the formulae are given, as you can see. You have that, they are very simple. Okay, you can compute theta m, you can compute z1, rho 0, rho naught, rho 1, z1, z2. You can calculate rho at theta is equal to 0 or omega t equal to 0. So just be keen on that one. That is if you will choose to do it for the CAT, but for the exam, definitely will not have much options. So I look forward to seeing how keen you are in terms of that. Any other question or comment?
I have a question.
Yeah.
is exciting TE11 the same as exciting TM11?
You look at the equations. The key is what is it that you want? Otherwise, if you are to draw it, you will be putting the probe just the same way, TM11, TE11. But if you want a maximum amplitude, then you look at the equation that are produced for a TM mode. You look at the function of H or E and look at what is it that you want to maximize on. Because the equations for H, X, and for TM and TE will be different. So you use the equations that you have for your design. But in the case of 1-1, most likely they are going to be the same position of the probe. But it's more of an optimization, or not really optimization, but what is it that you want to maximize? Is it E or is it H? Does that answer you? I don't know who asked the question. I didn't check your name.
Yes.
Yeah, you just look at those equations for TM and TE mode, and then you work with it. Whatever is given to you for this case, but in your lab or somewhere, then you know what equations you want to maximize. What is key is that you look at the position of the probe. So you look at the X, you look at Y, based on the size of the waveguide, which is the dimension A and dimension B. It could also be you are the one designing it. You're the one who wants to produce that. So you design. You say, I want this mode to produce this amount of power and this amplitude. So I'm making it this size. So you can make size A, you choose what it is, and size B, you use what it is. Okay. Any other question? Yeah, first semester is never easy to be exciting, but second semester is really exciting. So don't worry about it. I think we did it in the best way we could, but it's very hard to enjoy just devices, you know. Yeah, but those are the key elements of knowledge areas you need to have. If there are no further questions, then you can register your attendance.